Good morning from Austria. I will share my screen. I've slightly changed the title of my talk. I decided finally within the time to focus on single triplet qubits in silicon germanium heterostructures. And my goal is to try to give a rather pedagogical talk. So feel free to interrupt me during my presentation. So for people working with spin qubits in quantum dots, there has been one seminal paper in 1998, the paper of Loss Di Vincenzo, which suggested how effectively to use quantum dots or spins confined in quantum dots in order to move towards quantum processors. So the idea is, in principle, relatively simple. You take a spin, which here is indicated with an arrow, and what is in orange is supposed to be its wave function, confined in a quantum dot, which is a dashed circle. You will apply a magnetic field, you create a Zeeman splitting, which is equal to G mu BB in a first order if you assume that G is a number. And then by using microwaves, you can practically induce electron spin resonance and flip the spin. This is how you would do single qubit gates. And if you want to do 2 qubit gates in the field of spin qubits, practically you use 2 quantum dots, you bring them close to each other, then you can have wave function overlap, which leads to exchange interaction, and exchange interaction can lead to change of energies. And this is the basic mechanism of how you are going to do 2 qubit gates. If we go back to single qubit gates and understand a bit more how spin manipulation works, we have all learned at the university that first you need a large external magnetic field, a static one, and if we would write down the Hamiltonian, we would have 1/2 G mu BB sigma Z, and if we express it in the Larmor frequency, it is omega L sigma Z. So in order to induce electron spin resonance, you need a perpendicular AC magnetic field of smaller value, which practically points then, if the magnetic field is in the Z direction, it would point in the XY plane. And here it is written already in a form where you can see, as it's an oscillating magnetic field, it has a certain frequency, it has a certain phase and a certain amplitude. And if you do a bit of math and you go into the rotating frame, you can see how the Hamiltonian looks in the rotating frame. And when your driving frequency is equal to the Larmor frequency, practically you are left with this term. And then depending on the phase, you can decide whether you do X or Y rotations. So this is in some sense the conventional principle of electron spin resonance. And this is actually how the first spin qubit, Loss Di Vincenzo spin qubit, was realized back in 2006 by Frank Coppens et al. In the group of Leo Kauvenhoven. So it was the time still of gallium arsenide. You had a double quantum dot, and what Frank Coppens did, they deposited the polymer on top, and then they created a strip line. So this is nothing else than a metal through which you can drive an AC current, and an AC current creates a perpendicular magnetic field. While this work is beautiful, a challenge is how do you create local magnetic fields, because obviously creating local magnetic fields which would influence just this dot and not the other is a challenging thing. Another trend in the community, which was developed later on by Piero Ladier, was to use micromagnets, which create stray magnetic fields. And here the idea is that if you then move your spin within the gradient of magnetic field, this is equivalent to have an AC magnetic field. And finally, there is, in the early day works, there is the work in the group of Liv and van der Zijpen, where they have now, again, a very similar, possibly the identical device, in which they realize that actually for a system with non-negligible spin orbit, if you have an AC electric field, this actually translates into an AC magnetic field. Since then, a lot of things have happened. My group works with germanium. We are working with holes. So I would just like to give you a few slight introduction. What is different when you work with holes? what you see here is the standard band structure of germanium, where if we focus on the valence band, we have heavy holes, we have light holes, and we have the split off band, while on the upper part is the conduction band. So what is the difference when you work with holes? If we want to go on a very simple level and think of electrons in bulk in a system with negligible spin orbit, the Hamiltonian would be very easy. It would be h bar square k square over 2 times the effective mass. And what I show here in this cartoon picture is how a charge, which is represented by a blue ball, would move. And you see that this is the direction of motion, and there is no correlation between the spin degree of freedom and the motion. If now you go to holes, the upper part of the valence band is described by the Latinger-Cohen Hamiltonian, and you already see that it's quite a bit more complex, and this is already a simplified form for germanium. What you can see now for holes, that the direction of motion and the direction of the spin are locked to each other. Well, that's what actually spin orbit does. And it's becoming even more interesting when you move away from bulk, but you go towards two-dimensional systems, two-dimensional confinement. So from here to here, all what I've done is I've added a confinement in the z direction, which would be like I have created a two-dimensional Hall gas. And if you transform or you evolve the Hamiltonian, you will see that now actually the spin looks in the out-of-plane direction. In addition, what is interesting, the concept of heavy holes and light holes, one needs to be a bit careful, because in the direction of motions, the heavy holes actually have a light mass, while the light holes have a heavy mass. Thinking again, so what is the big difference when you do electron spin qubits and hole spin qubits? When we have a hole spin qubit or when we have a heavy hole spin qubit, we always think about a two-level system, but it's a heavy hole Kramer's doublet. And the big difference is that the whole wave function can be written as a superposition of a spin up and spin down states entangled with the orbital degree of freedom. So one needs to be aware when we say spin, in the case of holes, actually we mean pseudospin, because it is a superposition and it contains both spin up and spin down. So my group works with germanium. What is interesting or very nice with germanium, it has strong and electrically tunable spin orbit. A very nice thing for people working in academia is that it has a small effective mass, which means that we can create larger quantum dots, which for academic clean rooms is a blessing. Germanium has a large out-of-plane G factor. It is electrically tunable. That's a work during my postdoc time with the student I was working with at that time, Natalia Ares, where we could show that really by changing the electric field, we can significantly change the value of the G factor. Similar to silicon, also germanium can be isotopically purified. By now, there are very, very high mobility germanium quantum wells. And a very nice plus is that if you want to work with hybrid devices, it is rather straightforward to induce superconductivity via the proximity effect in germanium. So how are we going to do a qubit experiment in our germanium material? The general recipe, I would say, is rather simple. You confine two holes, you have a double quantum dot, you go to the last hole regime, then you need to find a way in order to do spin readout, you find the Larmor frequency, you do Rabi oscillations, and that is how you would really do step-by-step a qubit experiment. So let me briefly remind you the particle in the box. I told you in the slide before, we need to confine charges. So we all know the infinite potential well picture, which gives us eigenstates, which are in the case of an atom, besides being discrete, they're very much separated. M here, in the case of the atom, is the electron mass. For us, it will be the effective mass, and L is the width of the potential well. So the reason of the analogy between the atom And quantum dots is why very often you hear that quantum dots are called artificial atoms. So how do we transform this naive picture of the particle in the box in 1D in reality? These are the structures we are working with. So we have a germanium quantum well sandwiched between two layers of silicon germanium. And then we deposit a very thin oxide layer, about 50 nanometers by atomic layer deposition. And by E-beam lithography, we can define electrodes. And if you apply voltages to the electrodes, what I should point out here, in our case, the germanium quantum well, when there is no voltage applied to those electrodes, confine carriers. So if now you would apply a potential, you deplete all the holes in that part, and you stay with carriers in what will become the quantum dot. This is a top view of how typically our devices look like. So you have different layers written at different times. That is mainly for lithographic reasons, in order not to risk that your gates are going to be shorted to each other. And this gives you the possibility to have 3 quantum dots on one side and 1 quantum dot on the other side. This is the charge sensor, which allows us to do the spin qubit readout. Of course, then for the qubit experiment, one uses also arbitrary waveform generators, microwave sources, we apply magnetic fields, and our readout, in order to be able to read out fast, is done by RF reflectometry. So typically, how does an experiment look like? We tune up a double quantum dot, and then you move the 2 plungers, and you see the charge transitions. Now this is in charge sensing, because if it would be in transport, those lines you would not see. And if you scan a bigger range and compare with theory, you will indeed see that if your design is properly done, you can reach the last hole regime, and then you can really start counting how many holes you have in each quantum dot. And practically, how do you know that you are in the last hole regime? You stop at some point seeing transitions which would correspond to tunneling between the 2 dots, or between the dots and the leads. And then comes the idea, which was developed in the group of Seigo Tarucha by now many years ago. How will you read out a single spin? A single spin has a very small magnetic moment. It's very difficult to observe it. So the community does so-called Pauli spin blockade readout. So think now about the zoom in this stability diagram in this regime between 1 and 0, 2. Here I have put it in, I have used these symbols because it does not need to be 1, 1, 0, 2. It could be equivalent 1, 1, 0, 2. And the idea now is the following. When you are in point A, where you have the 2 charges in the same quantum dot, you are in a singlet state. You are in a singlet state because the triplet state due to exchange interaction is higher in energy, so we can neglect it, we can ignore it. If you are then in position B, so practically if you separate your 2 charges, now having 1 charge in the left dot, 1 in the right dot, you could be in 2 different configurations. So either you can have the spins anti-parallel or the spins parallel. And for the moment, let's ignore why from this configuration we could have reached the down configuration just by separating the spins. And then if we go back from the 1-1 configuration to the 0-2, which would be in position C, now if the spins are anti-parallel, tunneling will take place because the singlet is available. On the other hand, if in the position B both spins point down, then you cannot bring back the second spin because this is a triplet configuration, and as I told you, due to exchange interaction, the triplet is higher in energy. So this is the mechanism which is called spin-to-charge conversion. So effectively, the way we detect the spin is by detecting whether a charge has tunneled, yes or not. If the charge has tunneled, we know that the left spin, so we know that it was in a configuration that we form a singlet state, while no tunneling has taken place, is that the two spins form a triplet state. So now I will do a very fast detour. My group initially was not working with two-dimensional structures, about which I had been speaking about so far. We made the first germanium spin qubit back in 2018 with a structure which is called a hot wire. So this is a cartoon picture. What is here in dark brown is a type of a nanowire which has a height of 2 nanometers and a width of 20 nanometers. What you see here are source and drain. These experiments were done in current, by doing current measurements. And what we found out that as these structures were so shallow, just by putting a gate on top, the strain creates a quantum dot below the gate. So here, just having two gates, we could create a double dot. So you would have one dot here, one dot there. And we were able to do a germanium spin qubit. And at that time, we observed the fastest Rabi frequency. So that verified indeed that holes in germanium can be used as very fast spins for doing very fast spin manipulation. So we could reach Rabi frequencies extending 150 megahertz at out-of-plane magnetic fields of 127 millitesla. And then by doing a Ramsey experiment, we could measure the dephasing times, and we could reach dephasing times close to 200 nanoseconds. So that was a very encouraging thing to realize that indeed our system has strong spin orbit, but our dephasing times are actually already, these times are 10 times larger than what you get in 3.5 material. So the first spin orbit qubit in the group of Leo-Kauvenhoven showed a T2 star, or 3.5 materials show a T2 star of around 10 nanoseconds. By now, I should comment that the groups of Menno-Welters and Giordano-Scapucci have T2 star times of 20 microseconds. So germanium is a rather promising material. So what did we learn as a group from the first germanium spin qubit? We realized, well, that germanium is indeed a promising platform for the realization of electrically tunable spin qubits. You can have very fast spin manipulation times and decent spin dephasing times. What we also realized is that when you work with nanowires, it is rather challenging, because what I showed you here, I told you what's the positive aspect, that you need just one gate per quantum dot. But what was difficult to do is to tune the tunnel coupling between the two quantum dots. And when you want to go towards advanced experiments, tunnel coupling is everything. So this is a serious limitation. And also, if you want to have a charge sensor in such a device, that is as well technologically not trivial. While on the other hand, if you move to two-dimensional systems, with a cartoon being shown here, it is very straightforward to position a charge sensor, and this is what we then did. So I would say since 2020, the spin qubits in germanium two-dimensional Hall gases have seen a dramatic progress, driven significantly in the group of Menno-Welters in Delft. What you see here is the first spin qubit now in germanium in a two-dimensional Hall gas, and actually here they created a 2-qubit gate. 1 year later, they created a 4-qubit germanium quantum processor, and without going into detail to all the works which have been done, I jump forward to today. This is a paper which appeared on Archive this year by Nico Hendricks, who now leads together with Annemarie a quantum startup Groove. So you can see here 18 quantum dots and spin qubits. So those are not entangled, but it's a demonstration that indeed germanium has the potential for scale up. And on the right side, I show you a recent work of the group of Menno-Welters, where they have 10 quantum dots, 4 charge sensors. And actually here, they operated their quantum processor by making use of the fact that in germanium, the spin quantization axes are different. and I will comment on that at the end of my talk. So one of the big questions in the field is, okay, we can do nice n times n arrays, but how are we going to create really a scalable quantum processor? Let me remind you that with the error rate still existing, and if you think of using the surface code in order to create physical qubits, probably we are speaking about 1 million, 10 million qubits in order that you can start doing things which are, let's say, relevant for a real life application. So having 10 million qubits is challenging. And then there are many questions. How will you bring in DC lines? So I would say in most of the fields, also superconducting qubits are facing this challenge, also cold atoms. So going to a very large amount of qubits is a challenge. So one of the ideas which Lieven and Mark came up is that maybe the idea is to have n times n arrays, which are split on the wafer, and in between you can put maybe some quantum links and electronics to control that you don't need to have everything outside the fridge. So how can we envision such quantum links? Well, there are different ideas. One of the ideas is by taking or by looking what communities are doing, and this is a famous paper back in 2007 in the superconducting qubit community, where they use a superconducting resonator in order to couple two distant transmon qubits. And Lieven van der Zijpen's group has used a similar concept in 2024 in order to entangle two spins. Another idea which has become rather popular recently is to do shuttling. So practically you physically move the spin from one position to the other. So you would take this spin and you would move it to another quantum dot, which would be located several hundreds of microns away. If we want to use superconducting resonators as a quantum bus, we need to remember that superconductivity does not like magnetic fields, so it would be nice to be able to operate a qubit at low magnetic field values. So is this possible? So this is where I'm going now to focus on. I will introduce once more our material in a bit more proper way now. So the material we are working with is grown in the group of Giovanni Isela in the Politecnico of Milano. So they start with an intrinsic silicon substrate. Then they gradually increase the germanium content from 0% to 70%. So in this layer, there are plenty of dislocations, defects. Then they grow 2 micrometers of silicon germanium with germanium 70%. Then they drop the growth rate. They put 100 nanometers more of silicon germanium. Then we have our quantum well. Then they have a 20 nanometer silicon germanium spacer. And finally, they finish with a 1 nanometer silicon cup with the purpose of the silicon cup being in order to avoid the oxidation of germanium, as germanium oxides are rather nasty and one does not want to deal with it. So on the left side now you see really a TM. So actually our quantum wells have 97% germanium, and on the right hand you see now a scanning electron microscopy picture. This is a top view of what I've shown you before as a cartoon. So these are the electrodes, which are titanium palladium. Here you have the structure which will form the charge sensor. And in our early day devices, we had here a gap. We thought that by having the gap, charge sensing would be enhanced. That did not really prove to be true. And the additional difficulty was having that gap here made it more difficult to deplete our quantum dots. So by now our devices have a continuous, what we call here, backbone, which separates the charge sensor from the double quantum dot. Let's remember once more how the energy diagram of a double quantum dot looks like. So what I call here epsilon is nothing else than the detuning. So we have a double dot, we have a double well potential, and either you can have the two charges in two different dots or the two charges in the same dot. And the energy of the 2-0 is depicted as the red line, the energy of the 1-1 as the black line. And here, so far, I don't speak about spin. If I would think also about spin, the 2-0, I would also need to think whether the state with the two charges is in a singlet state or in a triplet state. But as I already mentioned before, we can safely ignore the triplet states because due to exchange interaction and for the energy scales in our systems, we can safely ignore the triplet state. So now here I have, in my naive cartoon picture, I have drawn a crossing, but the reality is, as we can have tunnel coupling between the two configurations, obviously that tunnel coupling opens up an anti-crossing. You still see one line which is not anti-crossed because this is the triplet 1-1. And if you have spin conserving tunneling, obviously the triplets cannot, so a triplet state and a singlet state, they cannot tunnel into each other. If now we apply a magnetic field, we can split the three triplet states, and this is now the energy diagram of a double quantum dot, and I tend to prefer to see it in that way. That's how I got used. And if you actually put the Hamiltonian into Python and you really calculate the eigenenergies, so in this cartoon picture here, I do not show you the avoided crossing because what before I omitted is that I told you that the singlet and the triplet cannot anticross, but when you have spin orbit, actually there can be spin flip tunneling, so there is a small anticrossing here. So how did we do our singlet triplet qubit in germanium whole gases? We fabricated the device, we cooled it down in a dilution fridge, we connected a fast lock-in to the reflectometry setup in order to be able to do fast readout. And what you see here is the measurements of Daniel Yirovets. It was actually during the COVID time, so while COVID, we were very lucky that the device was loaded 1 month before shutdown. So through remote control, Daniel could do measurements. So this is the charge stability diagram with an equivalent 2011. And then by applying pulses, the first goal was really to identify Pauli spin blockade. So indeed, you see this metastable triangle, which is an indication of Pauli spin blockade. So then how do we do our spin qubit experiment, our singlet triplet spin qubit experiment? We initialize in the singlet state, then you apply a very fast pulse to separate your two charges. If you apply a very fast pulse, you go over the avoided crossing. And now the difference is that here practically the eigenbasis, so the eigenbasis of your system has changed, which means that as your state is not anymore an eigenstate, you start getting coherent oscillations. So you stay at this point for a certain amount of time and then you pulse back. And depending whether you are in this state or in this state maps back to singlet, this state maps to triplet. Triplet leads to Pauli spin blockade. This is how you can really distinguish, and you can see the coherent oscillations, which you see here. So these are x-axis rotations. So this is the time you stay at this position. Here is the magnetic field, and you can clearly see coherent oscillations. And these oscillations are almost X-like because also in this position, though we have separated the two charges, still, so we are deep in the 1-1 state, we have not quenched completely the wave function overlap. So exchange interaction has not been dropped to 0. And that's what you see in this cartoon. So this is the delta G, the difference in the G factor between the two dots. And J has not gone to 0. If J would have gone to 0, practically we would really do rotation from S to T0. A very interesting thing, what we observed is that actually the G factor difference between the dots is 2, which is a very large value. Before and when you do this experiment with silicon, the difference in delta G is actually 2 10 to the minus 3. So due to the fact that we work with holes, the G factor difference is very much enhanced, and that's why actually we can operate our spin qubits at so low magnetic fields. So actually already at 500 microtesla, we can have a singlet triplet whole spin qubit. And as I told you, that if we would then use microwave superconducting resonators, 500 microtesla is a rather small magnetic field, which is suitable for such experiments. So here I show you X rotation. So how will I do a Z? Okay, and before that, just taking line cuts and proving that actually the coherence is not so bad. So at half a millitesla, our T2 star is 1 microsecond. So I told you our first germanium spin qubit had 200 nanoseconds. Now we have 1 microsecond. So we are improving. So how will we do exchange oscillations? So now you can do a different experiment. So again, you start from the singlet 2-0. You pulse very fast here. And now you allow coherent oscillation, but you want to do a pi half pulse. And once you have done a pi half pulse, you pulse back in order now to turn on exchange interaction, and exchange interaction leads to Z rotations. And these are the exchange oscillations you can see here. The coherence times depends on the tuning. And already seeing these measurements, you see that the rotation axes are not orthogonal, which means that makes it rather complex if you want to apply more complicated pulse sequences. And that's the big advantage of a loss Vincenzo qubit, that your manipulation axes are orthogonal to each other. So the question is, can we create a singlet triplet qubit with orthogonal axes? And the answer is yes. And in a second set of experiments, we move towards microwave-driven singlet triplet qubits. This is an experiment which Jaime did back in 2024, which was published in 2025. So you have a very similar structure. Everything is in principle the same, it's just different the way we operate it. So now what we are going to do is we start again with a singlet state. We are going to go this time very slowly over the anti-crossing so that we initialize in the lowest state. And when we are in the lowest state, we are going to apply a microwave drive in order to see what happens. Our initial idea of this experiment was actually to create a loss Vincenzo qubit in order to move to 2 qubit gates. But then what we saw actually a spectrum with 3 lines. Ignore these lines. So we saw 3 lines, and this is strikingly different to what Stefan Nudge-Perch saw in 2012. Again, this is a double dot. Actually, here you see 2 lines, and the explanation of these 2 lines is that you either manipulate the spin of the left quantum dot or the spin of the right quantum dot. Here, very clearly, we have 3 lines. Then we started reflecting, and we realized that actually in germanium, if you calculate what is the exchange interaction for a germanium quantum well compared to a silicon quantum well, you see that the exchange is significantly enhanced. So then we said, okay, if we have how can we understand if we have significant exchange interaction? So what Jaime did, no magnetic field, that would be the energy spectrum, that you would have the singlet state and the 3 triplets, which would be degenerate. And now with a microwave burst, you can create transitions between the singlet and the triplets. And this is what he mapped out for different detuning. And he could find out that actually exchange is very, very large. So it's around, it can be up to 700 megahertz or more. And when people do 2 qubit gates, typically you are with an exchange interaction of, let's say, when the spins are separated on a bit of in the range of kilohertz, low kilohertz. So actually what we see are not individual spins, but we see 2 spin states. So we see transitions between the T minus, the singlet state, the T minus, the T0, and the T minus, and the T plus. So if you want to think about it again, this plot, as we have here the magnetic field, this is the singlet state, which anti-crosses with the T minus. And as I told you, we initialize our system in the T minus, and then you see these 3 transitions. And as the magnetic field increases, the red So the three arrows increase in energy as you see it in our measurement. Similar work has been done also in the group of IBM. And now, as we see in the spectroscopy with 3 lines, we can also not just do the experiment in the in-plane magnetic field, that's the in-plane magnetic field, but we can do it also in the out-of-plane magnetic field. And the next step, of course, is then to do qubit measurements and measure the dephasing times. So here I summarize. So for in-plane, T2 star, we can see dephasing times reaching 3 microseconds, while for out of plane, for the singlet triplet out of plane, at 12 millitesla, we could measure a dephasing time of 400 nanoseconds. And the dephasing time strongly depend on the detuning on which you do the experiment. And in the last 2-3 minutes, I would like just shortly to comment that our microwave singlet triplet qubits, even if they might not prove to be the most useful qubits, they are a very nice tool for doing physics. When you work with holes, the quantization axis actually does not coincide the magnetic field because of the G tensor. So effectively, the quantization axis of a hole spin is given by the G tensor multiplied with the magnetic field. And it is known that for the in-plane directions, the spin quantization axes are very different. So if now you do a bit of geometry, let's assume that that's the quantization axis of the left dot, that's of the right dot. We can do a bit of geometrical projection. So that is the addition of those two vectors. We can also subtract the two vectors. And the interesting thing is that these quantities appear in the Hamiltonian of a double quantum dot system, which means that by doing the measurements we do, we should be able to extract delta theta, which is the difference in the quantization axis between the two quantum dots. And by doing a bit more considerations, you can see how that relates with those quantities. So by doing this, effectively by fitting our model to the transitions I just described before, and without going now too much in detail, you can see that we can extract the difference in quantization axis between the two dots. We can see that by reshuffling the gate voltages of our device. So we measured 3 configurations, and what you see here is the change in the voltages of each of the electrode compared to the initial configuration. And you can see that by reshuffling, one can really change the spin quantization axis angle difference. And if now one would think that one could use also AI, one could then really program the device in order to choose what's the quantization axis difference one would like to have or not. That was the last point I wanted to make. And I just want to advertise a review we wrote quite some time ago, which actually by now seems to be outdated, together with many colleagues. So I firmly believe germanium is a very promising platform. By now, I would say most groups work on planar germanium. And the idea at that time was to say by using planar germanium, you can create spin qubit systems. You can use superconducting systems. Actually, my group has realized a germanium gate tunable transmon device. And there are also ideas that one could use germanium in order to create minimal Kitaev chains to move towards Pullman-Majoranas. And then, of course, one can dream big of applications, simulations, emergence, and algorithms. And with that, before I thank you for your attention, obviously the work has been done by my group. The main results I presented are from Daniel Jirovec, who is now research assistant at the Technical University of Vienna, and Jaime Saez, who is currently postdoc with Lieven van der Zijpen. And with that, I would like to thank you for your attention. Thank you very much.
Thank you, Professor Katsaros, for this detailed talk. I now ask audiences if there is any question. I especially ask students to ask questions because this was a very detailed discussion.
So, Georgios, this is Shuddho here.
Hi.
Hello. Thank you once again for joining the workshop and this excellent talk. Actually, we badly needed an introduction to the whole system, because we've been dealing with electrons and didn't get much chance to have a review to start with on whole quantum. So I have actually lots of questions, and I'm also thinking if that encourages the students in the room to ask more questions. So I'll start with mine maybe. So part of the questions are related to, the system itself, because we know so little. First question is, so the samples that you get,
Yes.
does the well have purified or enriched germanium, or just natural germanium?
At the moment, we are still with natural germanium. We wanted to buy purified material. Then the war in Ukraine started. And as we know, science is not decoupled from politics. So at the moment, we still work with natural materials.
Thank you. And the related question was, I saw that the quantum well width is 18 nanometer, which very naively comparing with silicon systems is on the wider side. I mean, any rationale or just a choice?
Okay, the honest answer is that's what we started with. We believe now that actually we should maybe shrink it a bit.
Why so?
So it seems that 18 nanometers are at the limit of strain that material can take before, let's say, defects would be introduced.
I get it. Yeah, that makes sense. Absolutely. Bit on the the device turn on characteristics. I mean, I saw that you used an ALD oxide, which I'm not, of course, it's not here in the heterostructure. But is that oxide really needed?
Sorry?
Is the oxide really needed, or you could have put the gates directly?
So the difference to gallium arsenide is you don't have a Schottky barrier. So the risk for leakage, or at least we never managed to have a gate on top without getting leakage if we don't have an oxide.
But you do have the carriers, the holes to start with, or do you have to induce?
Okay, here is the mystery of germanium heterostructure. So the interface is sensitive to everything. So depending whether you do an HF dip or not before you put the oxide, depending on what oxide you put, some colleagues even tell us that depending on which resist you use when you fab, you can be on or off. In our case, we are always on. We have always carriers without applying gate voltage. And I myself, the early days, did an experiment. I did a whole bar or a whole bar structure just out of our material. I measured the square resistance, and then I just deposited aluminum oxide on top, and the resistance dropped by a factor of 4. So aluminum oxide is known to have fixed negative carriers, which for holes means it's like you apply a constant electric field.
That's right. I mean, which is a bad thing for silicon, but I guess for holes it's really helped.
So for many experiments, the fact that our heterostructures are on is nice because it makes life easier.
Absolutely. Yeah. A related question was, I'm assuming that omics is just putting down some metal, nothing else.
Yes. Also there we are lucky that so we do a soft ion milling, and then we put platinum, which is a very high work function, which for holes is what you want.
Yeah. Another question I had was more to do with the nanowires that you started with, and this is the time when I know you started working on the quantum dots. How did you actually do the Rabi oscillations here? Because you didn't have a sensor. And
this is really current readout, old school current readout. So it's Pauli spin blockade. So you pulse, you have the double dot, and you practically you bring the left dot in Pauli spin blockade. You do a rotation, you pulse it up, and then you integrate over a certain amount of time, and like this you measure a current.
Okay, and okay. So everything in current measurement directly, right? No sensor.
Yes, no sensor. And obviously this has limitations because you cannot extend your manipulation to long times, because as the current is charged over time and as we can measure up to a certain sensitivity, if the duration of your manipulation would be too long, the number of carriers per unit of time would become so small that you would not be able to measure it.
Understand. Yeah. And the final question is somewhat futuristic, and I thought I'll get your perspective. You say that the exchange interaction is very strong in, for the holes in germanium. So does
or
that,
can be at least very strong, and in our case it is, yes.
So does that mean that you see some obvious benefit for the latest in the field, the exchange only qubits?
So that's a good question. Indeed, our exchange interaction will be much stronger. So, okay, I need to reflect more, but indeed that might mean that there are some advantages compared to... the only question then would be, is there any real advantage using germanium over silicon, right? Because they seem to work very well.
Well, if the gates get faster, then why not? Because everything is controlling the exchange, right?
That is true. But then the question is, if exchange is too large, how much will you pay in the dephasing, right?
Yep.
I guess there is again a sweet spot thing here. I need to think more about it. It's a good question. I don't have an obvious answer. I will reflect.
Sure. Thank you. Thank you, Georgios.
Thank you very much.
Sure.
Okay, anyone else? Actually, I have a question. I'll go then. So in the last part of your talk, you said you can use, let's say, probably AI to choose the quantization axis of two different quantum dots, right? So at this point, you would apply different gate voltages. So that would necessarily limit you from controlling exchange or tunnel coupling, right? So you would be, by choosing a quantization axis, you would be kind of limited to one part of the exchange map or exchange. Is that
what one would need to see is, as the phase space is so big at some point, whether you can find positions where you can really have the quantization axis in the direction you want, and also other properties.
okay?
That's something to be seen, as the phase space is very gigantic. But in general, to me, the way I don't see any way around for whole spin qubits rather than using AI and teaching an algorithm and asking, I want delta G of this value and this tunnel coupling, and then the machine tries to tune up your device rather than a student, because that becomes really a routine and tedious work.
And have you tried some initial works in this direction?
Actually, we have a work together with a group of Natalia Ares. So a student of Natalia Ares came to my lab, and we have a paper on arXiv in which we have developed an AI, or they developed the AI algorithm together with my student Jaime. They implemented it, and we ran the algorithm. We told the algorithm to define a singlet triplet qubit and to go over 25 interdot transition, and it found 12 singlet triplet qubits. So you click it in the evening, you come back in the morning, and you have qubits at 12 different interdot transitions, and then you can compare properties. So I think there is a lot to do in this direction.
That's impressive, yes. Okay, I don't have any other questions. So if anyone else has questions? If not, we'll thank Professor Katsaros once again, and we hope to see you in person in the near future.
Thank you very much for the invitation. Have a good day. Bye-bye.
Bye. Have a nice day.